Welcome back to Applied Mathematics. In this video, we're going to be solving right triangles. This is the culmination of our discussion of trigonometry. We're going to be looking at how much information do we need in order to figure out the rest of the information available in a triangle. Although before we do that, we are going to need one more tool that we haven't discussed so far, and that is the inverse trigonometric function. A trigonometric function is a tool that we've been using that takes an angle and matches it to a ratio. An inverse trigonometric function is going to take a ratio and turn it into an angle. And so the idea here is fairly simple. For example, we know that the sine of 30 degrees is 1/2. So that means that if I want to take the inverse sine, I'm going to write the inverse sine. It's going to be a capital S instead of a lowercase s. And it's going to have a -1 power here. And since sine of 30 degrees is 1/2, the inverse sine of 1/2 is 30 degrees. Which is great if we already know the trig function, but that's usually not how it's used. Normally this comes up in the sense of I know the ratio and I don't know anything about the angle in question. Very often it's going to be something like I know that my tangent spits out a ratio of 2.35 over 1.46. So I go to my calculator, right? I have this triangle, I have this information. And the first thing you have to do with a calculator is think about degrees and radians. The first thing you have to do with a calculator is make sure the button actually turns the calculator on. There we go. Right. Again, pay attention to the indicator. My calculator is currently in radians. Based on what I did in the last problem, I think it makes more sense to have this calculator in degree mode. So let's go ahead and switch that over. My calculator is now in degrees, and I can use the inverse tangent. Right? Push the tangent button once, push the tangent button a second time, and now it says tangent raised to the negative first. That's the notation we use for inverse tangent, and punch in the stuff I have. 2.35 over 1.46. And my calculator is happy to tell me that this is 58.14828, etc., degrees. Again, degrees because it says degree measure right there. All right. Now the numbers that I punched in here each had 3 significant digits. And if we think back, 3 significant digits is round to the nearest 10th. So I'll round this angle to 58.1 degrees. All right, so this tool of the inverse tangent, we also have an inverse sine and an inverse cosine. Inverse, cotangent, secant, and cosecant exist, but they almost never come up. So I'm not even going to worry about them. Those of you who are moving onward to study further mathematics, those might come up in a future course. For right now, inverse sine, inverse cosine, and inverse tangent will take care of everything that we might want to take care of. All right. If we think about solving a triangle, every triangle has 6 pieces of information. The measures of each of the 3 angles, and the lengths of each of the 3 sides. In order to solve a right triangle, we're going to need 3 pieces of information. We need to know a right angle, we need to know that it is a right triangle, and we need to know which of the angles is the right angle in the right triangle. We need to know at least one side length, right? Every triangle given the same angles is in proportion to each other, so we need at least one side length to set the scale. And then we need any other piece of information. If we have a second side, we have everything we need. If we have a second angle, we have everything we need. And with that, we can find the 3 remaining pieces of information every time. Sometimes communicating what is in a right triangle is a little bit messy. And so our textbook uses a fairly standard notation. We're going to talk about triangle ABC with right angle C. And when we have this convention, we can draw a triangle, we can draw in where angles A, B, and C are. The usual convention is the length of each side is labeled by the opposite angle. So we have angle A on the left. The side opposite angle A has length little a. The side opposite angle B has length little b, and the side opposite angle C has length little c. The only reason for this convention is that it allows us to talk about a triangle very quickly without having to put a lot of detail into actually drawing something. It's better to draw the triangle. There are very few applications of trigonometry where you can't see a triangle drawn, but drawing a bunch of triangles takes up a lot of paper, and making homework assignments that are 20 pages long is intimidating, even if it's only 20 questions in length. Um, all right, so given triangle ABC with right angle C, if A is 42 degrees and C is 37 inches, we want to solve the triangle. All right, since we know we have triangle ABC with right angle C, we can draw this picture. We can mark in the things we know, and we can go from there. All right. In a triangle where you are given an angle, figuring out the other angle is pretty straightforward. Right? Angle B is 90 degrees minus angle A. And 90 minus 42 is 48 degrees. Now we want to look at the two unknown sides. All right, I'm going to mark this angle down to remind myself that I've found it, but I'm not going to write it in. A convention in solving right triangles is we always want to go to the given information and try to avoid using our calculated measures to calculate other things. Part of that is propagation of error. Every time we use a calculation, we've rounded and we've propagated our error a little bit further along. So going back to the original measurements is preferable. The other thing is error checking. If you go and do all the calculations from the original values, you can relate the values you get later on and check to make sure that nothing untoward happened. In this particular triangle, we're going to end up solving for two of the three sides. So we might use the Pythagorean theorem and check and make sure that our three sides are within reasonable approximation, satisfy the Pythagorean theorem. If you had a triangle where you had to calculate two of the angles, you would go back and you would look at adding the two angles together, or adding the three angles together, make sure you get 180 degrees as a quick way of double checking your work. All right. But I've got two remaining sides. Let's look at side A next. We've got angle A. We've got side C. We're looking for side A. In our trig functions, this is the opposite side. This is the hypotenuse. And the function that relates opposite to hypotenuse is the sine. Sine of angle A is equal to opposite side little a over hypotenuse little c. And I see that it's going to be 37 inches times the sine of 42 degrees will give me that last side A. I'm probably going to cover over that statement when I pull my calculator up, but I'm going to pull my calculator up and hey, it does just fit on the screen still. Pull my calculator up and punch that in. I have 37 times the sine of 42, double checking my calculator is in degree mode. That angle is given in degrees. Everything works out. I get that side A is 24.757, etc. But because 37 and sine of 42 degrees both have two significant digits, I will round this to two significant digits and call it 25 inches. Now, all that's left is figuring out side B. Compared to angle A, side B is the adjacent side, and I still want to go to side C, the hypotenuse, and not touch side A if I can avoid it, because I know that I just rounded, and so that little bit of error would propagate further, and that's not what I want. Right? So the trig function relating the adjacent side and the hypotenuse is the cosine. Cosine of A is little b over little c. So going to my calculator, I can punch in 37 times the cosine of 42 degrees, which I get 27.49, etc. I'll round that and call it 27 inches. All right, so with that, I have solved the triangle. Solving a right triangle involves finding three pieces of information I've got an angle of 48 degrees, a length of 25 inches, and a length of 27 inches. Those are the three things that I needed to figure out. I have figured them out. I have solved the triangle. All right. This was what I generally consider to be easy mode of solving right triangles. If you are given the hypotenuse and you are given one of the angles, that's the most straightforward way of having information to solve a triangle. It gets a little bit more complicated if you're given a side length instead of a hypotenuse, if you're given a leg. It also gets more complicated if you're given two sides and no angles, but those are two situations that we can figure out pretty easily. Okay, it's not challenging, but it's a little bit more involved. Let's take a look at each of those cases for two more examples. All right, sketching out my triangle. It is triangle ABC with right angle C. Let's say that this time I am given that, let's do angle B this time. Let's say I'm given that angle B is 66 degrees. And let's say that I'm given that side A is 380 millimeters. I need to figure out side B, I need to figure out side C, and I need to figure out angle A. Angle A is going to be pretty quick. Right, just 90 degrees minus the angle given to us, 24 degrees. That much is done. Figuring out the other sides is a little bit trickier. All right, let's go for side B next. Compared to angle B, side B is opposite, and side A, the 380 millimeters, is adjacent. And the trig function that relates the opposite side and the adjacent side is the tangent. Right? Tangent of angle B is little b over little a. Plug in what we know. And grab my calculator. I'm not going to put it on the screen. 380 times tangent of 66, my calculator tells me, is 853 and change. I've got stuff with two significant digits, so I'll round that to two significant digits and call it 850 millimeters. Then the last thing that I need to do is figure out side C. Side C is the hypotenuse of the triangle. We're given the adjacent side, and the trig function relating the adjacent side and the hypotenuse is the cosine. So I know that the cosine of angle B is going to be equal to side A divided by side C. Right? Side A is adjacent to angle B. So I plug in. And I realize that the thing I'm solving for is in the denominator of this fraction, which means that the algebra is going to be a little bit messier, but it's going to be okay. Multiply both sides of the equation by C. It looks a little bit goofy. C times the cosine of 66 degrees is equal to 380 millimeters. Then get C by itself by dividing, and we get that C is 380 divided by the cosine of 66. And my calculator is happy to do that for me. 380 over cosine 66 comes out at 934.26, keeping my two significant digits. I will call that 930 millimeters. All right, let's take a look at one more. Once again, we have triangle ABC with right angle at C. And I'm going to give us two sides marked at 87 feet and at 53 feet. And then one unknown side and two unknown angles. In this figure, figuring out the third side is fairly straightforward. That's just going to be the Pythagorean theorem. 87 squared is 53 squared plus our unknown b squared. My calculator is happy to tell me that 87 squared, rounded to two significant digits, is 7,600. And 53 squared, rounded to two significant digits, is 2,800. So b squared is 4,800, and taking the square root, we get that b itself is approximately 69. All right, so the third side here is 69 feet. I'll circle that, and I'll go on to think about the two angles. All right, compared to angle A, the sides that I have are the opposite side and the hypotenuse. Sine of angle A is equal to A over C, which means that A itself is the inverse sine of A over C. Right? That inverse sine, the new thing that we were talking about at the beginning of this video. All right, so I have the inverse sine of 53 over 87. I will pull my calculator back up. Try not to cover up what I'm calculating. Again, remember, for inverse sine, on my calculator, I hit the sine button twice. Some calculators, you'll hit the second key or an alternate key. But I have in here, in the inverse sine, 53 over 87. And my calculator is happy to accept that and give me that the angle in this case is going to be 41. And because my calculator is in degree mode, I know that that is 41 degrees. All right, two significant digits in those measurements, so I round my angle to the nearest degree. And then I can look at angle B. Well, compared to angle B, I have the adjacent side and the hypotenuse. So cosine of B is A over C, which means that B itself is the inverse cosine of A over C. I can punch that into my calculator using the same process. Scroll down the screen a little bit. Right, the numbers are the same. A is still 53. C is still 87. and I can take the inverse cosine of 53 over 87. My calculator is happy to tell me that that is 52 degrees. All right. Did I type that in wrong? I did type that in wrong. All right. I didn't mean to do this, but it's a great learning exercise. I said it when we started into solving right triangles that you always want to double check your work. And when you're looking at solving for two angles, one of the things we know, I come over this way, I can get out of the way of it. One of the things we know is that if you add this angle plus that angle, you should get 90 degrees. In this particular case, if you add these two angles together, you get 93 degrees. And that seems a little bit too far off. So I want to go back and double check my work. And I did go back and double check my work and realized that I typed it into my calculator wrong. I accidentally typed up here 57 over 87 instead of 53 over 87. So if I go back and I edit that and put the correct number in the numerator, I get instead 37.5, which rounds to 38, I guess. And now it does work out. If you add 38 degrees plus 52 degrees, you do in fact get 90 degrees. All right. It wouldn't surprise me if doing this, you end up looking at those angles and saying, oh, you add those together and you get 89 degrees, or you add those together and get 91 degrees. If you're off by one in the least significant digit, that's a rounding error. That's something is a little bit funny in the numbers you're looking at. If we had more significant digits, I would expect it to be closer. Right? If my measurements were given to 3 significant digits, then I would be writing all of these angles down to the nearest 10th of a degree, and I would expect that if you add them together, you'd get somewhere between 89.9 and 90.1. So the more information you have, the closer you expect things to get. But again, a great way of double checking and a good reason for thinking about going back to the beginning, because if I had just said that this is 41 degrees, I'd have gotten that the other angle is 49 degrees. I would have been off on both of them instead of having that tool that would give me the double check. In any event, that's all I have here. So try some practice problems, solve some right triangles, see where you get to with it, and I'll see you next time.